Swap two classical billiard balls, and you can track exactly which is which. But in quantum mechanics, identical particles completely lack individual identity. Because they are perfectly indistinguishable, exchanging their positions cannot alter any measurable property of the system. The physical probability density must remain exactly the same. Mathematically, we calculate that probability density by taking the absolute square of the wave function. As this equation shows, the squared wave function for particle 1 and particle 2 must perfectly equal the squared wave function of particle 2 and particle 1. But look what happens when we drop the squares. The wave functions themselves do not have to be strictly identical. As we remove the absolute values, the math allows the right side of the equation to pick up a complex phase factor, written here as e to the I theta. Standard physics curricula teach that this phase factor is rigidly set. It is +1 for bosons and -1 for fermions. We are going to prove that this division is not an arbitrary rule invented to make the math work. It is a strict geometric mandate of the universe. The relationship linking a particle's intrinsic spin to these +1 or -1 phase factors is codified in the spin statistics theorem. The physicist Wolfgang Pauli formalized this theorem, proving that the rules of particle exchange are deeply locked to the framework of relativistic quantum field theory. But the field theory proof is notoriously complex. Richard Feynman famously admitted to his students that the standard proof was so dense he could not reduce it to a simple intuitive explanation. To find that intuition, we have to temporarily abandon quantum field theory entirely. Instead of looking at the particles, we need to look at the shape of the space they move through. By examining the mathematical rules of space itself, we find that the strict division of all matter into either fermions or bosons is dictated directly by spatial topology. To see how space forces this rule, we use a mathematical mapping tool called configuration space. Rather than tracking absolute positions, this map only tracks the relative distance and orientation between two identical particles. We must account for hardcore repulsion, the physical reality that two identical particles cannot occupy the exact same coordinate point at the exact same time. In this 2D coordinate system plotting relative distance, that physical restriction tears a hole in the map. At the origin, a singularity is removed from the space. Exchanging particles draws a path halfway around it. A second exchange completes a 360-degree closed loop. The physics of particle exchange depends entirely on one geometric question. Can this closed mathematical loop be smoothly shrunk down to nothing without getting caught on that singularity? Our actual universe has 3 spatial dimensions. Let's add the z-axis back into our configuration space model. In 3D space, we have room to maneuver. The closed loop of our double exchange is lifted vertically off the 2D plane, slipped over the singularity, and shrunk down to a single point. Topologically, because the loop can be shrunk to 0 without getting trapped, a double exchange is identical to 0 exchanges. It is mathematically the same as doing nothing. This equation translates that topological reality into quantum algebra. Since 2 exchanges equal no change, our phase factor squared must equal exactly 1. Solving this yields only 2 roots, +1 representing bosons, or -1 representing fermions. There are no other options. The strict dichotomy of bosons and fermions is an unavoidable mathematical consequence of living in a universe with 3 spatial dimensions. So what happens to the laws of quantum mechanics if we restrict particles to a strictly 2-dimensional universe? This flat 2D grid contains our configuration space loop, but explicitly confined to the plane. Without a third dimension for a vertical escape, the tightening loop gets physically snagged and permanently trapped by the singularity. Because the loop cannot be shrunk to 0, a double exchange in 2D space is not topologically equivalent to doing nothing. We can visualize exactly why by using Richard Feynman's path integral formulation to track the particle's world lines over time. This space-time diagram contrasts 3D against 2D. In 3 dimensions, particle paths can easily bypass each other, but in 2 dimensions, as they exchange places, their world lines wrap around each other, forming a braided, intertwined pattern that cannot be untangled. Because these paths are permanently braided, the rule we established earlier breaks down. The phase factor squared no longer has to equal 1. Instead, the phase factor theta can take on any arbitrary fractional value. Particles restricted to 2 dimensions obey entirely new quantum statistics. They are no longer bosons or fermions, they are called anyons. Anyons appear in real 2-dimensional systems, like the fractional quantum Hall effect. Their existence proves that quantum statistics are entirely dictated by the dimensional topology they inhabit. Returning to our 3-dimensional reality, we are strictly locked to those 2 topological phases, +1 and -1. The spin statistics theorem bridges this geometry to physical matter. It maps particles with integer spin, like photons, to the +1 boson phase, and particles with half-integer spin, like electrons, to the -1 fermion phase. If we focus entirely on the electron's -1 phase, we can see how a simple topological minus sign constructs the periodic table. Look at this mathematical matrix, the Slater determinant, which frames multi-electron wave functions. Rows represent quantum states, and columns represent particle coordinates. If 2 fermions try to occupy the same state, 2 rows become identical. Linear algebra dictates the determinant is exactly 0. That 0 represents the Pauli exclusion principle. It is the physical impossibility of 2 fermions existing in the same state. This single topological rule prevents matter from collapsing in on itself, giving rigid structure to the entire universe. We have built this framework using abstract topology and algebra, but we can actually observe these invisible quantum statistics in a lab. The diatomic hydrogen molecule, containing 2 identical protons bound together, provides an ideal testing ground for identical particle exchange. Watch this rotating hydrogen molecule. As it spins end over end, the 2 identical protons exchange places, flipping the coordinate vector from r to -r. Because protons are fermions, your overall wave function must exhibit the antisymmetric -1 phase shift during this rotation. To satisfy that minus sign, the molecule is strictly limited in the rotational energy states it is allowed to occupy. This data chart shows the macroscopic result. These are the allowed rotational levels for parahydrogen and orthohydrogen gas. The intensity of the spectral lines follows a strict 3-to-1 ratio, exactly matching the predicted quantum multiplicities for fermions. The macroscopic heat capacity and the glowing spectral lines of a simple gas are the direct, observable fingerprints of the fundamental topology of 3D space.